Okay, hello class. Today in periods 3 and 4 we went over some but not all of this homework on series, so I'd like to go over the rest of it right now. And the last problem we did was number 20, and the first problem we didn't do is number 29. And I actually think that these problems, these 29, 30, 31, and 32 are actually maybe the most important ones from this whole homework, so it's a little bit of a shame we didn't get to it. Alright, the directions are all the same. Actually, I don't think I want to do all 4 of them. I think I'll do just 2 of them or something like that. I think I'll just do like 30 and 32 from this section, because they're kind of the same. And well, okay, what's the big idea? This sort of got covered today in class, but okay, well, let's just do it. Find the first, what is the problem? What is number 30? It says 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7 plus maybe I don't have enough room to do this, I don't know, plus 1 over and here we have 2n minus 1, 2n plus 1. 2n plus 1. And then plus ... Okay, so this is the whole subject of this section, infinite series. Here is a particular infinite series. And the goal, I guess, is to find out what the value of this infinite series is, to find out what it converges to. The first thing they say is to find the first 4 partial sums and suggest a formula for S sub n. Then find the sum of the infinite series by evaluating. Note that these series are not geometric. You cannot use the sum formula. Okay, so yeah, that's really the whole big idea, right? This is an infinite series, but it's not a geometric series. So I have no kind of formulas. I'm sort of on my own to use the actual definition of what it means for a series to converge. So let's do it. What is the sum of the first 1 term? Well, it's a third. What's the sum of the first 2 terms? It's a third plus 1/15, and that makes 6 fifteenths, which makes 2. Geez, what am I doing? Take out 3, so 2 thirds. No, take out 3, 2/5. There we go. Boom, 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 boom. Yeah, 5, 6, 15. Yep. Okay. What's the sum of the first 3 terms? Well, a third plus a 15th plus a 35th. That's just the sum of the first 2 terms, so 2/5, plus an extra 35th. Well, if I multiply by 7 over 7, that's 14. That's 15 over 35. And well, what is that? If I take a 5 out of the top and bottom, that becomes 3/7. Okay, and it says to do I'm starting to see the pattern, but it says to do the first 4 partial sums. So, I actually have to sort of think a little bit now, because they only printed the first 3 terms of this sequence, but in fact I don't even have to guess, because they gave me the general formula for the nth term of the series. But anyway, I think I get the gist. It's like 1, 3, 3, 5, 5, 7, 7, 9. So this is going to be 3/7 plus 1 over 7 times 9. Which is 63. So if I 9 over 9, that's 27. That's 28 over 7 times 9. So 7 cancels, and I get 4/9. Okay, this pattern now, I think, is very clear. The numerator is going up by 1 each time, and the denominator is going up by 2 each time. Okay, so now my job is to notice this pattern and to conjecture, and it really is only a conjecture, a formula for the sum of the first n terms. So if this pattern continues, and if I have understood this pattern correctly, then it seems that by the time I get to the nth partial sum, the numerator will be n, and the denominator will be, well, let's see, this is like the second odd number, the third odd number, the fourth number, the fifth odd number. So I guess this is like 2n plus 1. Let me just double check that. And yeah, that's just right? Plug in 1 here, you get 3, plug in 2, you get 5, plug in 3, you get 7, plug in 4, you get 9. Okay, so I want to stress the fact that I don't actually know for sure that this is the correct answer. I think that this is the correct answer. And what we learned just today is the principle of mathematical induction, which will enable me to actually prove, if I so desire, that this is the formula. So for the nth partial sum. Okay, but supposing that's right for them, it just must be right. Supposing that's right, then the problem just says, hey, find what the answer to this is. And okay, well, what am I supposed to do? I'm supposed to construct the sequence of partial sums. Sequence of partial sums. And okay, so in other words, the sum of the first 1 terms is 1/3. The sum of the first 2 terms is 2/5. The sum of the first 3 terms is 3/7. The sum of the first 4 terms is 4/9. And all the way out to the sum of the first n terms, I believe to be n over 2n plus 1. And this goes on forever. So we say that the series converges if the limit, if this sequence of partial sums has a limit. And what is the limit as n approaches infinity of the nth partial sum? Well, if the formula for the nth partial sum is n over 2n plus 1, then this is just easily seen. Divide the top and bottom by n, we see that this is 1/2. Okay, so this is kind of the big idea, right? I construct the sequence. I look at the partial sums. I conjecture a formula for the nth partial sum. I construct the sequence of partial sums, and I use my skills with taking limits of a sequence to determine what the limit of this sequence is. And if, as I keep adding more and more terms, the partial sums get closer and closer to 1/2, then I say that the series just is 1/2. Okay, hopefully that was pretty clear. Let's do one more that's just exactly like this. And, okay, so I won't be going over every problem from this homework, but I assigned all 4 of these. Maybe that was a little bit overkill, but we're going to go over just 2 of them. So, what's 32? This I remember being kind of the hardest one. So this is 3 over 1 times 4 plus 5 over 4 times 9 plus 7 over 9 times 16 plus, and once again they don't make me guess the pattern for the terms, because we might as well just give it as 2n plus 1 over n squared n plus 1 squared. Cha cha cha. Okay, question is, what is this? Well, once again, it's not geometric, so I can't use any kind of formulas. I just have to treat it each time like it's its own kind of thing. So, all right, let's do it. What's the sum of the first 1 terms? Well, it's 3/4. What's the sum of the first 2 terms? It's 3/4 plus 5 over 4 times 9. So I need to have 32 over 36. And what is 32 over 36? I guess you can take a 4 out of the top and bottom. So it's 8/9. Sure. Sure. Okay, what's the sum of the first 3? I don't want to make a mistake, because then everything is wrong. But yeah, that's just good. 27 over 30, yep. Okay, what's the sum of the first 3 terms? Well, it's going to be 8/9 plus 7 over 9 times 16. Oh boy. Okay, so I need to multiply by 16 over 16. It's not what I was expecting to happen. Well, okay, anyway, what is 8 times 16? 80 and 48 is 128. And 7 is 135 over, that's 144. Okay, but actually I see that 135 is 9 less than 144. So this is like 15 over 16. Because 15 times 16 is 135. Okay, and now what's the sum of the first 4 terms? Well, it's going to be 15/16 plus, what is the 4th term of this series? Well, they don't give it to me, but the numerator is going up by 2 every time. It's basically the odd numbers. And the denominator is like consecutive perfect squares. So therefore, the next term, the 4th term of the series, has a 9 on the top and 16 times 25 on the bottom. So I guess I can handle this. What's that going to be? I need to multiply by 25 over 25. Man, what's 15 times 25? Well, that's 250 and 125. That's 375. 375 and 9 is 384 over 400. Okay, but I can see that 384 is in fact 16 less than 400. So, that's like 24 over 25, I guess, right? Because 16 is going to go into 384 one fewer time than 25. Yeah, that's just true. Okay, so I got this now, I guess. Yeah, I just do have this. What is the pattern? It's going to be very close to 1. The denominators are growing by the perfect squares, and the numerator is always just 1 less. So therefore, the nth term of this series apparently is going to be n squared. On the bottom, no, a little bit more complicated than that, because the first partial sum is 2 squared, the second partial sum is 3 squared, so by the time I get to the 4th partial sum, it's 5 squared, so it's actually n plus 1 squared over, and the numerator is going to be 1 less than that. So n plus 1 squared minus 1. Okay, and I guess this could be kind of simplified a little bit as n squared plus 2n, then the 1's cancel, over n plus 1 squared. I don't know if that's worth doing. N squared plus 2n plus 1. Okay, sure. Maybe that's nice. Okay, if that is the nth formula for the nth partial sum, now what's my job? My job is to construct the sequence of partial sums. So I look at the sum of the first 1 terms, the sum of the first 2 terms, the sum of the first 3 terms, the sum of the first 4 terms, and all the way out to the sum of the first n terms, which is n squared plus 2n over n squared plus 2n plus 1, and on forever. That is the sequence, and now I have to ask the question, does that sequence have a limit? And I think the answer is just obviously yes, right? The limit as n approaches infinity of n squared plus 2n over n squared plus 2n plus 1 is, if you want to be kind of very serious about it, you can divide the top and bottom by n squared, which gives me 1 plus 2 over n on the top, and 1 plus 2 over n plus 1 over n squared on the bottom. But anyway, this limit is just definitely 1. You can even sort of see that the partial sums are getting closer and closer to 1. Therefore, this series just is 1. Okay, good. Hopefully by this point you have a very good understanding that an infinite series is just the limit of the sequence of partial sums. That's the whole thing we've been talking about. Okay, good. More things happening now. Shucks. Yeah. More things. Next page. These problems started getting a little bit harder if I remember. There's just a couple more. So, 35 says, hey, each side of a square has length 12. Okay, let me draw a big square here of length 12. Doesn't look much like a square. Jeez. Okay, great. Side length 12. Okay, good. The midpoint of the sides of the square are joined to form another square. Okay, so let's do that. Take the midpoint of each side and join them together to form another square. People have claimed in the past that this problem is like ambiguous, but there's just only one possible way to join the midpoints of the sides of the square to make another square, and that's it. This looks not such a great square, but okay, I'm okay with it. Alright, so what's going on here? The original side length of this thing was 12, so this was 12, but if that's the case, then now that we made these midpoints, these are both 6, okay, great. Okay, and then they just keep on doing this, right? So if this is 6 and this is 6, then math tells me that this is 6 root 2. So I'll label that 6 root 2. But then we come in with another, we just take the midpoints, again. So if that whole thing is 6 root 2, then half will be 3 root 2. And yeah, there's actually a theorem in general that if you connect the midpoints of the sides of a, never mind. Okay, so that means that this is like this, let's take a representative one, like maybe over here. This is 3 root 2, this is also 3 root 2, so then this is a 45, 45, 90 triangle, so then this becomes 6. Okay, so I think that's kind of good enough to appreciate the geometry of the situation. Each of these squares is going to be kind of like 1 over root 2 dilated times the previous one. I mean, I could even go one more step, I guess. If you want to go one more, if somehow that really brings it home, to do one more stage of this thing. That's 3 root 2, that's 3 root 2, so that's 6. But then, if I draw one sort of final square now, well, if that whole thing is 6, then that means that this is 3, and this is 3, and this is 3 root 2. Hope that's all good. Yeah. Okay. Well, great. So, now comes a bunch of questions. Question. If this process is continued indefinitely, so continue constructing these squares, forever. Find the sum of the areas of all the squares and the sum of the perimeters. Okay, well, so what happens if I add up all the kind of areas forever? Well, what's the area of the first square? It's just 12 times 12, so that's 144. Okay, what's the area of the blue square? Well, it's a square whose side length is 6 root 2. So 6 root 2 times 6 root 2 is 72. What's the area? What's the area of the red square? Well, it has 6 on the side, so it's 6 times 6, so that's 36. And the green square is 3 root 2 on the side, so 3 root 2 times 3 root 2 is 9 times 2 is 18. Okay, so I think we already now see that that this is geometric. And what are we multiplying by each time? By 1/2. So 1/2, 1/2, 1/2. Okay, and therefore, I just simply use the formula for the sum of an infinite geometric series. And the answer is this is going to be a over 1 minus r. So 144 over 1 minus 1/2, which is just 1/2. So it's 288. And that's just the answer to that problem. Okay, on the other hand, let's consider the perimeters. What are the perimeters? Well, now the perimeter of the first square is going to be 12 times 4, so that's 48. What's the perimeter of the blue square? It's 6 root 2 on the side, so 4 of those, so 24 root 2. What's the perimeter of the red square? Well, that's 6 on the side, so that's 24. What's the perimeter of the green square? 3 root 2 on the side, so 10 so that's 12 root 2. And yeah, I think we see now that what are we doing? We're dividing by root 2 each time. And so the common ratio is 1 over root 2. 1 over root 2, 1 over root 2. Okay, and that's kind of what I said already a few minutes ago. That actually that is the best way to kind of understand these squares. Is that for each square, its side length is kind of like half the diagonal of the previous square. That's how I think about it, right? Take the original square. What is this 6 root 2? It's half of what the full diagonal would be. So it's the diagonal is root 2 times as much. So this is like root 2 over 2 times as much, otherwise known as 1 over root 2 times as much. Okay, anyway, what is this perimeter then? I just, again, use the formula. So this is going to be 48 over 1 minus 1 over root 2. And you could leave it like that, but that's kind of disgusting. So the professional thing to do is to rewrite this by getting a common denominator in the denominator first. So that would be root 2 minus 1 over root 2, which is then 48 root 2 over root 2 minus 1. That's looking a little bit better, but what most people do in this situation is they multiply by the conjugate of root 2 minus 1 to clean up that denominator a little bit. And if you do that, you get 2 minus 1 in the denominator, so that's just kind of gone. And so actually the answer to this problem is just the numerator. 48 root 2 times root 2 is going to be 96. And then plus 48 root 2. So maybe that's kind of an indication of why people like to kind of simplify all the way, because sometimes you get something sort of really nice like that. Okay, that's 33. We're going to do 37 and then maybe stop. But maybe not. Okay. All right. Yeah. Okay. Good. 37. All right. This is a kind of fascinating and amazing problem, which brings together several of the things that we've been doing. So here is exactly what it says. It says, let S sub n is the nth partial sum. Is the nth partial sum. And S is the limit of the following geometric series. S is the nth partial sum, and S is the limit of, and then they give you a series. The series is 1 plus a half plus a fourth plus an eighth plus forever. Okay, so that is kind of a, and then they ask what is the smallest value? What is the smallest value of n for which S minus S sub n is less than 0.0001. Oh boy. Okay. How should we even kind of begin here? Well, okay. Here we're given a particular infinite series. So if we're given this particular infinite series, let's take it seriously. By the way, they say S is the limit of. In other words, they're sort of defining S to be, what you get when you add all these up. Okay, well, what is S anyway? Well, this is an infinite series. It's geometric. So let's just calculate what S is. S is going to be, well, it's the first term, 1 over 1 minus, and what is R? R is half. Okay, so this is 1 over half, so this is 2. Alright, so that's maybe kind of obvious that S is 2. So that's one good thing to know. Then they also refer to the nth partial sum. What is the nth partial sum? Well, again, it's geometric, so again I have a formula. It's A, which is 1, times 1 minus R, which is a half, to the n over 1 minus R, where R is a half. Okay, well that makes, again, a half down here in the denominator. So really this is like 2 times 1 minus 1 half to the n. And so perhaps we should just write this nth partial sum as 2 minus 2 times 1/2 to the n. Okay, well, great. Having written the partial sum, the nth partial sum this way, I think it's pretty clear what's going on, right? Because as n goes to infinity, one can see at a glance that, when you multiply by 1/2 times itself, like 1,000,000 times, then this is basically going to 0, and that shows that this limit is indeed 2. Okay, so that's just a basic understanding of kind of this problem. So really, when they say what is the smallest value, okay. So once I know that s is 2, then maybe I'm going to rewrite this thing that they're asking for. What are they asking for? They're saying, all right, what is the difference between 2 and the nth partial sum less than 1 over, and I think that's 10,000. Okay, that's what they're asking. Well, does this sound like anything to you? This sounds like something to me. This sounds something like a challenge. They're saying, I dare you to make the gap between s and s sub n less than 0.0001. What we are now doing is connecting what we know about limits and epsilon n proofs of limits to the fact that we've defined a series as a limit, specifically a limit of partial sums. Okay, so let's make a picture to try to kind of understand this. So this is similar to the pictures that we were making when we were studying limits. So I feel very strongly that the answer to this problem is 2. I mean it just is 2, right? And so what I'm going to now do is I'm going to plot the partial sums. So what happens when I add the first partial sum? Well, the first partial sum is 1, so I get a boom. What happens when I add the second partial sum? Well, 1 plus 1/2 is 1.5. Okay? What happens when I add the third partial sum? Well, 1.5 and 1/4 is like 7/4. And so in fact, in each case, I'm going to get a little bit closer. And the actual claim that is being made here is that this is a plot of the partial sums, after all. What we are really claiming here is that that this limit is what we're really claiming here is that this series converges to 2. Of course, our formula for the geometric series tells us that the series converges to 2, but using just the definition of what it means for a series to converge to a value, what we need to show is that the partial sums kind of go to 2. And so bringing it all the way back to the level of prove to me that the limit of this sequence of partial sums really is 2. Well, how do I do that? Well, we have a whole system for that, right? You challenge me with some kind of epsilon, and if I want to prove to you that the limit of the sequence of partial sums is 2, then I go out far enough in my sequence of partial sums such that beyond that point all of the partial sums are within 2. So that's what's happening here, right? What they're basically saying is, dude, how far out in the sequence of partial sums must you go for the difference between the nth partial sum and 2 to be less than 1 over 10,000, say? So in this particular case, the epsilon challenge is 1 over 10,000. And what do I have to do to meet that challenge? I have to add enough terms of my sequence. I don't know how many. I have to add a lot of terms until the nth partial sum. If you maybe put it another way, if you really think that this is 2, which it is, then what you really mean when you say that this is 2 is that despite given any challenge whatsoever, like 1 over 10,000, I can add up enough terms of this series so that the nth partial sum is as close to 2 as you demand. Okay, putting that all together then, I think I know what to do. Because what is 2 minus, well, the nth partial sum, we just made a formula for it, right? It's 2 minus 2 times 1/2 to the n, and I want to know when that is less than 1 over 10,000. So this whole problem just boils down to when is 2 times 1/2 to the n less than 1 over 10,000. And, okay, I can divide by 2. So I get 1/2 to the n is less than 1 over 20,000. And now I really just need to solve this inequality. And here this is sort of begging to be reciprocated. So this says, when is 2 to the n greater than 20,000? And, alright, now I just need to know my powers of n. I'm not sure that, powers of 2, I'm not sure I really can get all the way up to 20,000. Man, I thought I could. What do I know? I know that 2 to the 10th is 1,024, and then there's 2048, and then there's 4,096, and then there's like 8,192. And then the next one is like going to be 16 something, and then the next one will go over. Yeah, so that's 2 to the 11th, that's 2 to the 12th, that's 2 to the 13th, that's 2 to the 14th. Okay, so if I counted that correctly, 2 to the 14th is 16,000 something, so 14 is not enough. But if n is greater than or equal to 15, then this will be true. And so the answer is that, in fact, that I have to go out to 15. The smallest so the answer to this problem is 15. Why is 15 the answer? Because 15 is the smallest number such that the gap between 2 and the 15th partial sum is finally so small that it's less than this challenge of 1 over 10,000. Okay, if I'm at the 14th partial sum, if I have 14 terms of the sequence, then the difference between me and 2 is very, very small, but it's not quite small enough. Okay, and then of course beyond that point also the gaps will just get smaller and smaller. Okay, so this was a great problem kind of connecting at kind of a theoretical level our understanding of the definition of a limit, the eps given an epsilon challenge, finding an n which meets that challenge, but also connecting the fact that the value of a series is really a limit of a sequence of partial sums, and so, okay. I think that's good. I'm going to stop this video now. The next problem, number 38, is just exactly the same, but you just have to now do it yourself. And then there's this little calculator exercise, which I think I will make its own little standalone 10-minute video. So, goodbye. Okay, hello. Is that somehow maybe better? That is better. Okay, here we go. There's this homework problem, which said, this was called computer exercise, and yeah, they came right out with it, and they told you, hey, consider the following series: the sum from n equals 1 to infinity of 1 over n. And unfortunately, they just tell you that this diverges. But they say very slowly. So the question they asked is, sort of how slowly, and they wanted you to write a kind of a computer program. I think you can do this in 5 lines or something like that in Java. So I think you are all able to do this. Okay, what is this series again? This is the series when n is 1, you get 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus, I want to go out pretty far, I think, plus 1/8 plus 1/9 plus 1/10. Should have written smaller, plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16. Okay, and on and on forever. Okay, great, I guess. This is the this is a series. This is an infinite series. And okay, let's just suppose for a moment that they didn't ruin it by telling you that this thing diverges. You might be thinking, well, okay, I got this under control. It's not geometric, so I don't have a nice little formula for it, but what can I say about it? Well, first of all, notice that the terms of this series form a harmonic sequence. Because what is a harmonic sequence? A harmonic sequence is a sequence whose reciprocals are arithmetic. So the reciprocals of all of these terms, this would be 1, 2, 3, 4, 5. And so this is not, and therefore we call this a harmonic series. What's a harmonic series? It's the sum of an infinite number of terms of a harmonic sequence. And it is in some sense like the simplest, most basic harmonic series because it's just the sums of the reciprocals of the natural numbers. Therefore, people call it the harmonic series. So whenever anyone says the harmonic series, they're talking about this one. Though technically there are a whole bunch of series that you could call harmonic. Okay. What can we say about this? Well, this is, I think, very, very fascinating because we are adding up an infinite number of terms. So that sounds dangerous. But on the other hand, we've already seen cases in which, say, 1 plus a half plus a fourth plus an eighth plus a 16th, for example. Well, here I'm also adding up an infinite number of terms, but those terms are getting smaller and smaller. And in fact, this is just 2. So if I add up a bunch of terms starting with 1 plus a half, and each time I add a number which is half the size of the previous term, even though I'm adding up an infinite number of terms, somehow magically I just get a finite number, which is 2. But with the harmonic series, something else happens. And here, look, we're adding up, terms which are getting smaller and smaller. So you should feel some sort of tension here, which is, look, I'm adding up things which are getting smaller and smaller, but I'm adding up an infinite number of them. And so it's unclear what happens when you add up an infinite number of things which are nonetheless getting smaller and smaller. And the answer is, in this case, that this thing diverges. But it diverges very, very slowly. And the problem from the packet said to write this program, to sort of brute force it and to ask, how many terms do I need in order, so sort of how 1 plus a half plus a third plus a fourth plus etc. How far out do I have to go in order for that to be bigger than 3? Okay, and the answer is, this was part A. The answer is 11. All right, so if you add up 11, it takes 11 terms of this sequence, or you have to go out to the 11th partial sum in order for it to be bigger than 3. Okay, how far out do you go in order for the sum to be bigger than 4? All right, well, answer 31. Yikes. So because the terms are getting smaller and smaller, I need sort of more and more of them to make any kind of progress. And it's not until the 31st partial sum that the terms of this it's not that only at the 31st partial sum is the 31st partial sum will be bigger than 4. Not until then. And then the last question is, all right, well, how many terms do I need in order for the sum to be bigger than 10? And the answer is 12,367. That is, I think, kind of just mind-boggling. I need to add up 12,367 of these reciprocals of the natural numbers just for the sum to be, 10. And yet, though this series grows very, very slowly, it does in fact go off to infinity. Okay, now that was all you had to do for homework, but I will now show you, this is going to be just like a proof, that the harmonic series diverges. And okay, the proof kind of goes like this. Okay, so first of all, let this be S. Let's just call this S for the moment. Alright, and now I'm going to make a new thing called S small. And S small is going to be constructed in such a way that it is guaranteed to be smaller than S. Alright, less than or equal to. Okay, so here's the strategy. First, you just copy that 1 right down. Okay, and then 1/2, you also copy the 1/2. But for 1/3, let's make 1/3 smaller. So a number smaller than 1/3 is 1/4. But for this 1/4, I'm just going to copy it down. Okay, what about 1/5? Well, for 1/5, I'm going to convert it into 1/8. For 1/6, I'm going to also convert it into 1/8. 1/7, I'm also going to convert into 1/8. And 1/8, I'm going to leave alone. So notice, what am I doing here? I am taking every single number from the original series, and I'm either making it smaller, I'm either leaving it the same, or I'm making it smaller. Okay, and what about 1/9? I'm going to write as 1/16. 1/10 I'm going to write as 1/16. And all of these are going to be 1/16, all the way up to 1/16. Okay, if you're following what is going on here, this is genius. Here's what I'm doing. I am changing the 1/3 to be 1/4. But then, what is 1/4 plus 1/4? It's 1/2. I'm changing 1/5, 1/6, 1/7, and 1/8 to all be 1/8. But when I add up 4 of these 1/8, well, that's also a half. Here, I'm changing the 16 numbers between 1/9 and 1/16 to all be 1/16. And so, S small is revealed to be really 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2, and in fact, this just goes on forever. Okay, what happens if you add up 1 and a half 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 and a half? Well, this just diverges. This 1/2, this 1 plus a half plus a half plus a half is getting bigger, forever. And so if this is going off to infinity, well, then this thing is in fact a little bit smaller than the thing I actually care about. And so if this small thing is growing on and on to infinity, then my series is going to infinity as well. So that is the proof that this diverges. It diverges because it's even bigger than something which is becoming infinitely huge. Okay, and then sort of a final kind of comment on this, which is a huge preview of something you're going to do next year. You might ask, at what rate does this diverge? And if that's your question, it's a little bit hard to determine exactly. So instead, let's take a look at S small, because S small is not so different from S. It's going to be a little bit smaller, but not that much smaller, because we're tweaking it only very slightly. Okay, so looking at this S small, what's up with this S small? Well, I can graph it. So let's kind of make this graph now. So here we go. So, and okay, well, by the time I'm on the first term, I'm already up here at 1. Then by the time I'm on the second term, that's 1 plus a half. So that's 3 halves. Okay, so boom, boom. Okay, how far out till I get to 2? Well, I now need 4 terms to get to 2. Okay, how many terms do I need to get to 2.5? Well, to get another half of growth, I now need 4 more terms. So I need to go out to the 8th term in order for the sum to be 5 halves. Okay, how far out do I go? Do I need to go in order for the sum to be 3? Well, I need I need to go all the way out to the 6th. No, I've done something wrong. 1.5, 2.5. I think I need to go all the way out to the 16th. Oh yeah, that's right. I need to go all the way out to the 16th term in order to clear 3. Okay, and maybe you sort of see what's happening here, right? Each time I need to get another rise of 1/2 out of S small, I need to go out double as far. If I want to hit 3.5, how am I going to get an extra half out of this? Well, it's going to be 1/17 plus 1/18 plus 1, it's going to all the way out to 32. So I need to get to 32, I need to go out to the 32nd term in order to hit 3.5. Okay, so what kind of curve is like this? What is the curve which grows at a what is the curve? What is the curve which, to achieve a constant increase in output, requires an exponentially increasing distance along the x-axis? And the answer is, that's just what a logarithm is. This is in fact just the inverse of an exponential. Instead of growing exponentially, it takes exponential increase along the x-axis for this function to achieve constant change along the y-axis. Okay, and yeah. So therefore, it seems that the actual, well, okay, maybe I'll just leave it at that, right? S small is roughly the nth partial sum of S small is growing sort of logarithmically. And so actually that gives some kind of understanding now for why this diverges so slowly. This diverges so slowly, I'm giving sort of more detail to this. It's not just that it's diverging slowly. In fact, it's diverging sort of as slowly as a logarithm grows. Logarithms are among the most slowly growing formulas that we have. And I've just shown how the growth in this S small series is precisely logarithmic. This is just some kind of log base 2 type thing. And this S, our actual series, is just a tiny bit more than that. Okay, goodbye.